Hi everyone and welcome. In today's video, we are going to take a look at a very famous proof, Euclid's proof on why there are infinitely many prime numbers. It's a pretty short proof, but it's a little bit delicate, so we're going to make sure that you really understand what's going on. So let's get started. The theorem that we're going to prove in today's class is that there are infinitely many prime numbers. So to begin this proof, let's suppose for contradiction that there exists finitely many prime numbers. Let's suppose there are n of them. So we can create a list. We can label the first prime as P1, second prime as P2, and all the way up to Pn. Okay, so this is my list of all the prime numbers. Every prime number is supposed to be on this list. Now, the idea behind this proof is to somehow show that this list is incomplete. That is, we're going to show that there are always numbers, prime numbers missing from this list. Okay, so there should be a brand new prime number that we're actually missing from this list. We begin by constructing a brand new number, let's call it n, and the way this number is constructed is by multiplying all the prime numbers together and then adding 1. Okay, so just take all the prime numbers that we have in our list above, multiply them together, and add 1, and that's how we get n. Now remember that a prime number is just an integer greater than 1. Okay, and then if you multiply integers together, the result is an integer. If you add 1 to it, the result is still an integer. So n is just an integer greater than 1. Okay, now by the fundamental theorem of arithmetic, either n is prime or n can be written as a product of prime numbers. Well, if n is prime, then this prime number is way bigger than every prime on our list because we're multiplying all these integers greater than 1 together, adding 1 to it. So yeah, n is going to be larger than every individual component, each individual prime. So this is a brand new prime number that's not on our list. And so therefore we get a contradiction. So now let's take a look at the second case. Let's suppose that n is not prime, but instead it can be written as a product of prime numbers. Well, if n is just a product of a bunch of primes, then it's also going to be divisible by one of those primes, right? There must exist some prime that divides n. Just take one of those primes in that factorization and let that be q, right? So there exists a prime number that divides n. Well, now the question is this a prime from our list, right? It should be ideally from our list. So let's see what happens. If this prime number is from our list, then it's just one of the primes, right? It could be like P7 or something like that. It's just one of the PIs for some I. Well, then I claim that Q divides the product P1, P2, all the way up to Pn, because, this is just, Q is just one of the PIs. So it's going to cancel with one of the PIs over here, and you get a result which is integer. Okay, so that's why Q divides this product. Well, if Q divides n and Q divides this product, then Q should divide the difference of these two numbers, right? Q should also divide the sum and difference of these numbers. In particular, Q divides the difference. But what is the difference? Remember, n was just the product plus 1. N was just the product plus 1. So we're doing n minus the product. The products will just cancel out, and this difference is equal to 1. So in other words, Q should divide 1, right? Q should divide 1. But that's not possible because Q is a prime number greater than 1, like 2, 3, 5. So it cannot divide 1. It cannot divide 1. That's your contradiction. If that still doesn't seem clear to you, then take a look at this down here. Let's take n, which was the product of all the prime numbers, plus 1. And try dividing it by q. Try dividing it by q. So that means you have to divide this entire side by q. But then that means you can divide each component, each term by q. Now the first term will be divisible, right? Because q is just one of the primes on this list. It's just going to cancel with one of the primes, and so this will be an integer. But this is the problem. 1 divided by q is not going to be an integer because q is some number bigger than 1, like 2, 3, 5. So this is not going to work. So therefore, q does not divide n, right? Q does not divide n. This is a contradiction. Okay, so we suppose that q was a prime number from our list, and we got a contradiction. So then that means that q is a prime number that's not on our list, right? Q must not be on our list. Well, if q is not from our list, then there you go. You found a brand new prime number, and there's your contradiction. No matter what case we try, we always get a contradiction. And so therefore, there has to be infinitely many prime numbers. The reason why these contradictions are arising is because of our assumption that you can make a list of finitely many primes. So that's not possible. In fact, there are infinitely many primes. Another point that I would like to highlight here is that this number n that we created here is not guaranteed to be prime. Okay, it might be prime, it might be composite. In fact, it doesn't matter. Either case, you're always going to get a contradiction, right? If it is prime, then there you go. You got your brand new prime number not on the list. Okay, if it's not prime, then it's going to have a prime divisor q. And we ended up arguing that that prime divisor q cannot be on your list. Okay, so in either case, you can see that there are prime numbers missing from our list. And that's how you complete the proof. Okay, and that brings us to the end of today's video. I hope you enjoyed this short proof. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.